So in our agenda, we're first going to discuss what a force is and what all the types of forces are that we're going to go through in this course. We're also going to practice drawing some free body diagrams. We're going to introduce Newton's first law and do some practice problems around that concept. And then you'll have time to complete your quiz and do your homework. So what is a force? A force is simply just a push or a pull. The unit of force is the Newton, or capital N. Since forces have both a magnitude and a direction, they are vector quantities. Forces are what make objects either speed up or slow down. So let's look at some of the most common forces which we're going to use in this course. First, the force of gravity, or Fg for short. Fg, you'll see, is equal to mg. Now this is a formula that you'll see on your formula sheet. Fg stands for the force of gravity, m is the mass of the object in kilograms, and g represents the gravitational constant, which is equal to 9.80 meters per second squared. Okay, so this is a constant. You're always going to use this value. This value is correct for any question where you're located near the surface of the Earth, which is what we're going to be doing in this course always. Okay, so the force of gravity is always pointing towards the center of the Earth. So that would be straight down. Okay, so in every question, we will always have a force of gravity. Every problem we deal with will have this force because all objects have a mass. Okay, and g is always going to be 9.80 meters per second squared for the purpose of this course. So each question will always have a force of gravity that we have to consider. The next force is the normal force. This is the force that's exerted by a surface onto the object, keeping the object from falling through the surface. So for example, let's say my hand here is a table and I put a pen on the table. There is a force of gravity acting on this pen. It always points straight down. If that was the only force acting on the pen would be falling. So there must be an equal and opposite force acting on the pen, holding it up. That force is the normal force. It's the force exerted on the pen by the table below it. Okay, so that force is always normal or perpendicular to the surface. In this case, it would be pointing straight up. If my table was like this on an angle, my normal force would then point in this direction, perpendicular to the surface. Okay, so it's always going to be perpendicular to the surface that it's on. And the force of gravity always points straight down, no matter what angle the surface is at. If the object is not in contact with a surface, there will not be a normal force. Okay? Let's look at the next force, tension. So tension is the pulling force acted on an object by a string or a rope. And it's always acting in the direction of the rope, pointing away from the object. So for example, here I have a string, and on the end of the string is a ring tied to it. So the ring is my object. I'm holding the string. There's a force of gravity always that's exerted on this object, pulling it down towards the center of the Earth. But if that was the only force acting on the object, then the ring would be falling. So there must be an equal but opposite force holding it up. The ring is not on a surface, so there is no normal force, but there is a tension, a force of tension, because the string is holding it up. And that force of tension is pulling it up and pointing upwards. Okay? So if there's no string or rope in a question, then there is no tension that you have to consider. The next force is the applied force. So this is the type of force, if you see in a question that they say somebody or something is either pushing or pulling an object, that would be an applied force. That's how you would label it, as F applied. The next type of force is the force of friction, or F sub F. The force of friction always opposes the motion of the object. Okay, so it's always going in the opposite direction that the object is actually moving. If you want to calculate the force of friction, you first have to calculate the normal force. And that's because the equation for the force of friction, which will be given to you on a test or an exam, is equal to the coefficient of friction. This right here, mu, is the coefficient of friction times the normal force. So we first need to calculate the normal force before we can calculate the force of friction. Now, the bigger the coefficient is, the bigger the force of friction is. What's the coefficient mean? So all that means is that it's giving us an indication of how rough the surfaces are with each other. So let's say I have a hockey puck and I'm sliding it across a sheet of ice. When I'm sliding it across, the two surfaces are relatively smooth compared to one another. So when I slide it, it's really easy to slide it across. So the coefficient of friction between a hockey puck and ice would be pretty low, a pretty small number. Now, if instead I'm moving, let's say, a piece of wood across a piece of sandpaper and I'm rubbing those across each other, it's quite a lot harder to rub those things across each other, to slide them past each other, because they're rougher surfaces. So the coefficient of friction between wood and sandpaper would be bigger. The normal force all depends on how heavy the object is. So if we're talking about an object that has a bigger mass, like a piano, compared to an object with a smaller mass, like a pen, we would see that the piano would have a bigger normal force. And so both the coefficient of friction and the normal force are affecting the force of friction. The bigger the coefficient is and the bigger the normal force is, the harder it is to push an object. That's why it's a lot harder to push a piano than it is to push a pen across the table, okay? The coefficient of friction is typically going to be given to you in a problem, but if it doesn't mention coefficient of friction and it doesn't mention friction at all, then you can just assume there's no friction in the problem and then ignore it altogether. Okay, so now we're going to talk about how to draw free body diagrams. A free body diagram is just a schematic representation of all the forces that are acting on an object. We're always going to represent our object as a dot, and each force vector is always going to begin at the dot, moving away from it in the direction that the force is going. The length of the vector represents the magnitude of the force. So the bigger you draw your vector, that is indicating that the force value is bigger as well. We can assign positive directions by drawing the x and the y axes on our diagram as well. Okay, so let's do some examples. You throw a ball into the air. Draw a free body diagram of the ball after it has left your hand. Okay, so let's say I'm throwing this object. It's in the air. While it's in the air, what are the forces acting on it? Okay, so we're going to begin by first drawing the ball. Every object we're going to represent as a dot, no matter what the object is. So this dot is my ball. Now, what forces are acting on the ball? So let's go through all the forces that we discussed already. So the first force is the force of gravity. There will always be a force of gravity, and it always points straight down. So let's put that one in. So this is my force of gravity right here. Okay, now let's go through all the other forces and see if any of those exist in this diagram. So the next force was the normal force. Okay, so the normal force only exists if our object is on the surface. So when we throw a ball into the air and it's in the air, there is no surface underneath that ball. So there would be no normal force. Okay? The next force that we talked about was the force of tension. So if we have a string that's pulling our ball or any object or a rope, then we would include it. But in this case, there is no string or rope, so we're not going to include it. We also talked about the force of friction. The force of friction is only relevant in a problem if it actually uses the word friction in the problem, which in this problem, there's no mention of friction, so we're going to ignore it as well. We also talked about the applied force. And for an applied force, you would have to have mention in the question of somebody or something pushing or pulling the object. And in this case, there is no such mention, so there is no applied force. Okay, so there's really just one force acting on the ball. It doesn't matter whether the ball is on its way up, whether it's at its maximum height, or if it's on its way down. In any case, it only has one force acting on it, and that would be the force of gravity. Okay, second example. You tie a string around a ring and hold the free end of the string. Draw a free body diagram of the ring. Okay, so this is the example that we already spoke about before. We have a ring, it's being suspended by a string. So we're going to draw a free body diagram. First, we'll draw a dot to represent our ring. And now let's think about all the forces acting on it. So we always have a force of gravity, so let's put that in. Force of gravity always acts straight down. And now, if that was the only force acting on the ring, it would be falling down. So there must be another force that's keeping it from falling. It's being pulled up by a string. So there's a force of tension. So I'm going to call that T for tension. That's my tension force. It's equal in magnitude to the force of gravity, but it's going in the opposite direction, keeping the ring from falling down. Third example, a dog is sitting on the ground. Draw a free body diagram of the dog. Okay, so for this one, again, I'm going to represent the dog by just drawing a dot. There's always a force of gravity, which always points straight down. So this is my force of gravity. And again, if this was the only force acting on my dog, the dog would be falling through the ground, which it's not. It's just sitting there. So there must be a force that's equal to the force of gravity acting in the opposite direction. Now, which force would that be? The dog is sitting on the ground. It's on a surface. Anytime there's a surface, there would be a normal force. And the normal force acts perpendicular to the surface. So we're going to assume that our surface is level, it's horizontal. So then our normal force would act vertically upward. So this is my normal force over here. Okay, so there's no friction mentioned in this question, so there's no force of friction. There's no ropes, so there's no tension. There's no mention of anybody or anything pushing the dog, so there's no applied force. All right. Next example, you are pulling a wagon at an angle of 30 degrees above the horizontal. Draw a free body diagram of the wagon. Okay, so again, our wagon is represented by just a dot. We always have a force of gravity, and it points straight down every time. Now, it says you are pulling the wagon at an angle of 30 degrees. So we're pulling this wagon. That's somebody or something applying a force on this wagon. So this would be called the force applied. It's at an angle of 30 degrees above the horizontal. So this would be the horizontal over here. So at an angle of 30 degrees above the horizontal would mean something like this. So now this force, I'm going to call it my force applied. Are there any other forces acting on this wagon? So the wagon, we have to assume, is on a surface because it's on the ground. You're pulling it as it's on the ground, you're pulling it at an angle and it's moving along the ground. So there must be a force that the ground exerts on the wagon. That would be the normal force. So I'm going to draw the normal force. The ground is horizontal, so the normal force would point straight up. Okay, there is no string or rope in the question, so there's no tension. And there's also no mention of friction, so that's why we're not including the force of friction here. Okay, example 5. You're pushing a piano across the floor. The friction between the floor and the piano makes it hard for you to push it. Okay, so let's draw a free body diagram. This time we're drawing the free body diagram of our piano. We're still going to represent it as a dot. The first force we always can put in is the force of gravity, and it always points straight downwards. Let me do that again. My piano is a dot. The force of gravity points straight downwards, Fg. Now, what other forces are there? Okay, so the second force that we talked about, I believe, was the normal force. That's if the object is in contact with the surface, which it is. The piano is on the floor. We're assuming the floor is horizontal, so the normal force would be perpendicular to that, holding the piano up. So it would look like this, the normal force. Okay, then there's also mention about friction here, so there must be a force of friction in this question. It says the friction between the floor and the piano makes it hard to push. So we don't know which way this piano is moving, but let's assume it's moving this way, okay? So if the piano is moving this way, then the force of friction must be opposing that motion, so it would go the opposite direction. The force of friction. Okay, if we think of the other forces we talked about, there was tension. There is no tension in this question because there's no string or rope. There's an applied force as well. Now in this question, should we include an applied force? You are pushing a piano across the floor. So yes, there should be an applied force because you're pushing the piano. So which way would the applied force go? Well, we've already said that the piano is moving this way. There's a reason why it's moving that way. It's because you're pushing it that way. So this is the direction of the applied force. So that's my force applied. Okay? All right, now we're going to go over Newton's first law, which states that if there is no net force acting on an object, it will continue to move at a constant velocity. Now, what is a net force? And what does it mean when an object has no net force? Net force just means the unbalanced forces. And if it says that there are no net forces, that means there are no unbalanced forces. So for example, we have a dog sitting on the ground. It has a force of gravity going down, and it has a normal force pointing up. Those two forces are equal in magnitude but opposite in direction, so they'll cancel each other out. And in the end, there will be no net force, zero net force. They're balanced completely, so it's zero net force. If, for example, I have a ball and it's falling, the only force acting on it is the force of gravity, and that force of gravity is pulling it down. There is no other force acting on it. So that has a net force. The net force is not zero because this force of gravity is not balanced. It's not canceling out with another force. Okay, so no net force means there is all the forces are being balanced. If you have a net force, it means there's an unbalanced force that doesn't get canceled out. Okay? So what we're saying with Newton's first law is that if there is no net force, so in an example like this, no net force acting on an object, it will continue to move at a constant velocity. So for example, if this dog over here is at rest, it will continue to stay at rest forever as long as there is no net force. If the dog is initially moving at a speed of 1 meter per second, and the free body diagram looks like this, where there is still no net force, it will continue to move at 1 meter per second in the same direction forever. Okay? So thus, if the object was initially at rest, it would remain at rest. But if it was initially moving at a velocity, such as, for example, 3 meters per second left, it will continue to do so. If you know that an object is moving at a constant velocity, or that it's at rest, which means the velocity is constant at 0, then that means it's in equilibrium, which means all of the forces cancel out and the net force is 0, like it is here. Okay, so let's check to see if you understand Newton's first law. So we're going to do a multiple of true and false questions, and we'll discuss whether these are true or false. If they're false, we'll correct the statements. So first, If there is no net force acting on an object, it must be at rest. Is that true or is it false? Okay, so that one is false. Let's correct the statement. If there is no net force acting on an object, it must have, I'll erase this, it must have a constant velocity or be at rest. Okay, so if an object has no net force acting on it, then that means it either has a constant velocity or it's at rest. It doesn't mean it has to be at rest. So that's why this statement was false. Okay, so next question. An object that is at rest has no net force acting on it. Is that true or is it false? Okay, so if an object is at rest, then that means that it must be in equilibrium because it has its velocity is constant. If you're at rest, your velocity is 0 and it's constant. It's staying 0 all the time. So then that means you must have no net force acting on you. So this would be true. Okay, so your net force is 0, which means all your forces all cancel each other out and balance out. Next question. If there is no net force acting on an object, its velocity must remain constant. True or false? Okay, so if there's no net force acting on the object, again, all of the forces are balanced out, so its velocity must be constant. That's correct. Next question. An object that is moving at a constant velocity has no forces acting on it. Is that correct? No, it's false. So if an object is moving at a constant velocity, that would imply that it has no net force acting on it. So if I put in the word net, that would correct the statement. It has no net force, but that doesn't mean it has no forces. Okay, so something that's moving at a constant velocity has forces on it because every object has a force of gravity at least. So there must be forces acting on it, but they all balance one another out. So there's no net force. If the net force on an object points to the right, does that imply that the force of friction has to point to the left? Okay, so this one is false. If your net force is pointing to the right, that doesn't mean the force of friction is going to point to the left. What's true about the force of friction is that it always opposes the motion. Okay, it doesn't oppose the net force, it opposes the motion. So I'm just going to erase this part, scratch it out, and I'll replace it with if the motion of an object. If the motion of an object points to the right, the force of friction must point to the left. That is true, not the net force. Okay, so let's do some examples here. So a 10-kilogram dog is lying on the floor. Draw the free body diagram of the dog and calculate the value of each force. Okay, so similar to what we did before, but now we're going to actually calculate all the values. Okay, so we're first going to draw the free body diagram. We have a dog. We're going to represent it with just a dot again. The first force that we can always consider is the force of gravity, because that one's always there and it always points straight down. So I'm going to draw that one. So this is my force of gravity. Now the equation for the force of gravity is Fg equals mg. We want to calculate this value, so the mass has to be in kilograms. So kilograms is the standard unit SI unit for mass. So we have to have it in kilograms. If it's in any other unit, you need to convert your units to kilograms. So my mass is 10 kilograms. And G is 9.80. The units for G can either be meters per second squared or newtons per kilogram. They're both equivalent units. I'm going to write it as newtons per kilogram because that way you can see that the kilograms cancel out and you're left with the units for force, which is newtons. So when I multiply 10 times 9.80, I get 98.0 newtons. Okay, so that's my force of gravity. But my dog is lying on the floor. The dog is on a surface. And anytime there's a surface, there's always going to be a normal force. So let's draw that. So here's my normal force. Now because my dog is stationary, it's lying on the floor, it is not falling through the floor. That means that the force of gravity and the normal force need to balance one another out. So whatever I got for the force of gravity has to equal the normal force. So I'm going to write it in. My normal force then has to be 98.0 newtons. It's just pointing in the opposite direction. Okay, so I drew a free body diagram of my dog with the two forces, but I also calculated the value of each of those forces. Okay, next example. You push a 10 kilogram box across the floor with a force of 30 newtons. The coefficient of friction between the box and the floor is 0.2. Draw a free body diagram of the box and calculate the value of each force. So first I'm going to draw a dot to represent my box. So this is my box. And what forces are acting on it? So there's always the force of gravity pointing straight down. So this is my force of gravity, and Fg always equals mg. M is the mass of my object, so in this case my 10 kilogram box has to be in kilograms, and G is my gravitational constant, which is always 9.80 meters per second squared, or newtons per meter. Newtons per kilogram. My kilograms cancel out, and I end up with 98.0 newtons, just like my 10 kilogram dog. Okay, so it's being pushed across the floor with a force of 30 newtons. Okay, so I'm pushing the object. So I'm going to assume I'm pushing it this way. And I'm going to call this my force applied. And it's equal to 30 newtons. So that's my F applied. The coefficient of friction between the box and the floor is 0.2. Now I can't find my force of friction until I find a different force, and that would be my normal force. So you can't have friction unless you have a normal force. So let's find a normal force first. Since the box is on the floor, it's on a surface, that means there will be a normal force. The normal force always acts perpendicular to the surface. So I'm going to assume my floor is horizontal, so my normal force is pointing upwards. There are no other forces acting up or down in this question. So that means that the force of gravity and the normal force must balance each other out. Otherwise, my box is either going to fall through the floor into the ground, or it's going to fly up into the sky. That's not happening. It's staying on the surface. So the two forces, the normal and the force of gravity, must cancel one another out. They must be equal in magnitude, but opposite in direction. So my normal force then has to be 98.0 newtons pointing up. Okay. So now I have my force of gravity, my normal force, my applied force, and there is mention of friction in the question. So since friction is mentioned, I need to consider it. And friction always opposes the motion. So I'm pushing a box in this direction, so I chose to draw that it's pushing to the left. I'm pushing it to the left, so my box is moving to the left. So then that means the force of friction opposes the motion, it would be going to the right. So it would be going this way. This is my force of friction. Now how do I calculate force of friction? It always equals mu, which is the coefficient of friction, times the normal force. In this case, they tell us that the coefficient of friction is 0.2. Oops. And my normal force I found over here is 98 newtons. So 0.2 times 98. So I get 19.6 newtons. So now I have all of the forces acting on the box. I calculated all the values. So I have my force of gravity, 98 newtons, my normal force, 98 newtons, my force of friction, 19.6 newtons, and my applied force, 30 newtons. So I have all my forces. The only other force that is not here is the force of tension, because there is no rope or string in the question. All right, let's do this next example. You're pulling a 2 kilogram wagon at an angle of 30 degrees above the horizontal with a force of 30 newtons. Draw the free body diagram of the wagon and then calculate the value of each of the forces. Okay, so again, we're going to do the same thing. We have our wagon, which we're going to represent as a dot. One of the forces is always going to be the force of gravity, so let's do that one first. So I have the force of gravity, which always points straight down. The wagon is on a surface, so that's why we're going to have a normal force. We're going to assume that the wagon is on level ground, so the normal force would point straight up. Now we're pulling the wagon, let's say I'm pulling it this way, at an angle of 30 degrees above the horizontal. So if this is my horizontal here, I'm pulling it at 30 degrees above the horizontal. So this is 30 degrees. And the force of me pulling it would be called the applied force. Now there's no rope or string in the question, so we're not going to have a tension, and there's no mention of friction at all in this question, so we're not going to include friction. Okay, so that's it. Those are all the forces acting on my wagon. Now we're going to actually calculate everything. So Fg always equals mg, where m is the mass of the object in kilograms, so in this case it's 2 kilograms. And G is 9.80. Newtons per kilogram. The kilograms cancel one another out, and I get 19.6 newtons. Okay, so that's my Fg. My F applied, the question tells me my F applied is 30 newtons. Okay, so that's right here. It tells me I'm pulling the wagon at an angle of 30 degrees with a force of 30 newtons. So this is my force applied, is 30 newtons. Okay, and then I have a normal force. So most people, when you ask them, when I say, what is the normal force here? They would say that it equals 19.6 newtons, okay? But it's not. And the reason for that is because in this question, if these two were both equal but opposite, you would be left with this F applied here. And do you see how the F applied has two components to it? It has an x component, a horizontal component, which we'll call x, and it also has a vertical component, which we will call y. Now, if these two forces were to cancel out, the normal and the force of gravity, we would still be left with a y component of the F apply. We'd have this y component here, which means that our wagon would be flying up into the sky, and we don't want that to happen. We want to make it so that all of the y components cancel one another out. Okay, so sometimes we could have an object that is moving in one direction, but it is not moving in the other direction. Usually it's the y direction. A lot of times objects move in the x direction, like a wagon that you're pulling across the ground. In the y direction, it's not moving, it's not going up and down, but it's moving in the x direction. So what we want to do is we want to make it so that all of the y components cancel each other out. So we're going to calculate the y component of this F applied, and we're going to find the normal force so that all of the y components cancel out. So first, let's find this y component. Okay, well, here we have a right-angled triangle. My angle is 30 degrees, and my F applied, which is my hypotenuse, is 30 newtons. I'm looking for the y component. I'm going to call this F applied y. Okay, so it's the y component of my F applied. It's the opposite side of my 30 degrees. So if I'm looking at SOHCAHTOA, opposite side means I'm going to be using sine. So it would equal the hypotenuse, 30, sine of my angle, 30. Okay, so that's what this F applied is equal to, 30 sine 30 in newtons. Okay, so on my calculator I'm going to type up 30 sine 30 and I get 15. So my F applied in the y direction is 15 newtons. All right, so now I'm going to find my normal force. I know my force of gravity is 19.6 pointing down. I know that my y component of my F applied is 15 newtons pointing up. So what does my normal force need to be so that all of the forces in the y direction cancel out? Again, we don't want to have a net force in the y direction, because if we did, the wagon would be flying up into the sky or falling through the ground. Well, we don't want it to do that. So what force does this normal force need to be? Okay, you might be able to think about it in your head and figure it out. I'm going to write it out this way. I'm going to say the F net in the y direction. I'm going to say that positive direction would be upwards, okay, because we're talking about the y direction. So positive is up. I want to make it so the net force in the y direction is 0. That way all of the forces in the y direction cancel out, and this object is not changing its velocity in the y direction. It's staying constant. It's staying at a velocity of 0 in that direction. It's only moving in the x direction. So let's write down all the forces that we know in the y direction. We have the normal force. It's pointing up, so it's going to be positive. We have the force of gravity, which is pointing down, so it's negative. And we have the y component of the F applied, which is pointing upwards, so it's positive. So I'm going to write F applied with a little y next to it. Those are all the forces that are going in the y direction, up and down. They all have to add up to be 0 so that they can cancel each other out. So let's put in all the values. My normal force is what I'm looking for, so I'll keep that as it is. My force of gravity is 19.6. And my F applied y is 15 newtons, and it's pointing upwards, so it's positive. 15 newtons. All of that has to equal 0. I'm going to solve for my normal force. Negative 19.6 plus 15 is negative 4.6 equals 0. I'll move that to the other side. F normal equals 4.6 newtons. So that's the value of my normal force. Okay, I could figure out what my x component of my F applied is, but I don't really need to because I don't need it for anything. I just want to know what all the forces are. So now I know my Fg, force of gravity, is 19.6 and it's pointing down. I know my F applied is on an angle of 30 degrees above the horizontal and it equals 30 newtons. And I know my normal force is pointing up and it's 4.6 newtons. So I've answered the question. Okay, here's another question. You're pulling your sister on a sled with a force of 250 newtons at an angle of 18 degrees above the horizontal. The coefficient of friction between the sled and the snow is 0.35. If the combined mass of your sister and the sled is 54 kilograms, draw the free body diagram and then find the value of all the forces. Okay, so let's start drawing. So we're starting with my sister and the sled. That is how we're going to represent we're going to represent those two, the sister and the sled, as this dot. Okay. So the first force we always put in is the force of gravity. That one points straight down. And we can calculate it. Fg equals mg. The mass of my sister and the sled is 54 kilograms, so that's my m. 54 kilograms. My g is 9.80 newtons per kilogram. I'm going to type this up. 54 times 9.80, and I get 529.2 newtons because my kilograms cancel out. Okay, so I'm done with my Fg. Next, my sister and the sled, they're on the surface of the snow. So there is going to be a normal force. I'm pulling my sister on the sled with this force at an angle of 18 degrees above the horizontal. The coefficient of friction is given, and they don't mention anything about the ground being at any angle. Okay, I'm pulling my sister on the sled at an angle, but the ground is not given as being at any angle. So I'm going to assume the ground is level. So if the ground is level, my sister and the sled are on the surface of the ground, so that means that there must be a normal force acting perpendicular to this level surface or horizontal surface, so it would be pointing upwards. This is my normal force. Before we can calculate this normal force, we need to see if there are any other forces here that have y components in them. Okay, so we have an angle of 18 degrees above the horizontal. Okay, so this is me pulling my sister on the sled at an angle of 18 degrees above the horizontal. So this force is the force applied. Okay. It tells me that the force that I'm pulling my sister in the sled is 250 newtons, so that's my force applied. Okay, so I have a force of gravity in every case. I have a normal force because my sister and sled are on the surface, on the snow. I have a force applied, and then they also in this question mention the coefficient of friction between the sled and the snow is this, 0.35. So there must be friction. So I'm pulling my sister at this angle. She's coming towards me, okay? So when you pull a sled, the sled doesn't lift off the ground. The sled is sliding across the ground. Just like when you pull on a wagon, on the handle of a wagon, you pull it at an angle, but the wagon moves horizontally. So the sled is moving in this direction. This is the velocity of the sled, moving to the right in this case. So if I'm going to put in my force of friction in here, it would oppose the motion. Sled's moving to the right, force of friction would then go to the left. If I wanted to, I could have made my F applied go to the left, and then my force of friction would go to the right. Okay, so now this is my force of friction. Now the equation for force of friction is force of friction equals the coefficient of friction times the normal force. So I can't calculate this yet until I find my normal force. To get this normal force is just like the question we did last with the wagon. I want to make sure that this sled is not falling into the ground or flying off the surface of the ground. We want it to stay on the ground. So that means the net force of the sled in the y direction has to be 0. So I'm going to do this on the side again. So I'll say the positive direction is defined as upwards. The net force in the y direction is equal to 0. So let's list off all my forces in the y direction. I have the normal force, which is Fn. It's going upwards, so it's positive. I have my force of gravity, which is pointing downwards, so it's negative. And I have the y component. This is my x component. This would be my y component of my F applied. So I'm going to call that positive because it's pointing upwards. F applied in the y direction equals 0. So my F normal is what I'm looking for. My force of gravity I already found is 529.2 newtons. And my F applied in the y direction, let's do it here. F applied y. Okay, again we're going to use SOHCAHTOA. My y direction is opposite of my 18-degree angle, so I'm going to use sine. So it's going to be my hypotenuse, which is 250 sine of my angle, 18 degrees. So I'll type that in, 250 sine of 18, and I get 77.3. So I'm just rounding right now. 77.3 newtons. Okay, so that's my F applied y. It's pointing upwards, so I'm going to put it right here. 77.3 newtons equals 0. I'm solving for this Fn, so I'm going to bring everything else to the other side. Let's add these together first. So I have negative 529.2 plus 77.3, and I get Fn minus 451.9 equals 0. Fn equals, I bring this to the other side and I get positive 451.9 newtons. Now I know my normal force. So that's what's going to go in here. Okay, now we need to calculate our force of friction. So our force of friction is the coefficient of friction, which is given to us in the question, 0.35. Coefficient of friction has no units in it, times the normal force, 451.9 newtons. So I'm going to just multiply 0.35 times 451.9, and I get 158.2 newtons. So now we have all of our forces. So I know my force of gravity is 529.2 newtons. My normal force is 451.9 newtons. My F applied is 250 newtons. And my force of friction is 158.2 newtons. All right, and now we have our homework. So the homework is not listed here, but if you go back to Blackboard, if you go to the notes section on the homework page, you could see all the homework problems that you can do with a description for each. All right, so I hope you enjoyed this lecture. Have a great week, and I'll see you next week. Thanks.